having a few question and answer portion at the end. And if we still have time at the end, then after the fifth speaker, then we will have some discussion. And also we'll be going to present some of the results of the survey that we sent out to the investigators before this summit. So just to see the feedback so far and how we can improve the management of this hub and moving forward. After which, after this afternoon session, we will have some social networking drinks. It will be probably at the foyer. So I would like to invite everyone to please stay, and we will have some drinks for 1 hour after this. Anyway, thank you very much for staying over, and we can start now for the first speaker for this afternoon. So the first speaker is Professor Michael Duke. He is one of the chief investigators. He is the chief investigator from Victoria University with the Institute of Sustainable Industries and Livable Cities. He has worked for 22 years in materials and applications research on membrane technology for sustainable foods processing, resource recovery, and water energy saving applications. Professor Duke is also the first recipient of the inaugural Tony Fain Award for his outstanding contributions in membrane science and technology from the Membrane Society of Australasia. He is also a former panel member of the Australian Research Council College of Experts, the founding president of the Membrane Society of Australasia, and currently co-editor of the International Journal Desalination. And he is also currently the president of the World Association of Membrane Societies. That's a lot. Please welcome Professor Michael Duke.
Just for a 200-word bio, wasn't it? Oh, thanks, Leonard. It's a great pleasure to be a CI on the hub and sort of joining in and being able to contribute and collaborate together. And congratulate Sean, Leonard, Shurub, and Ibrahim and the great work that you guys are doing to bring us all together. And good luck, and we look forward to working together. So as you heard from Leonard, there's a lot of membrane in my bio, and I actually do have a slide about the wonderful things about membranes. Yeah, there's more to come. Anyway, so what I was going to talk about is demonstrating innovative technologies, membrane technologies for industrial wastewater treatment and supporting the circular economy. So what I've done is I've assembled a few projects that we've done in the past with some industry partners, and very applied. There's not much science in those, but there's more in those with the papers, or if you want to talk to me about those, I'm just going to touch on them briefly and talk a bit about the project in which we're going to embark on as part of the NiCE Hub. And does this go forward? No. I just push the... I'll just click here then. Okay. So yeah, we've heard a lot about the circular economy, but I wanted to make a particular point about resource recovery and circular economy, resource recovery supporting the circular economy that can progress when there's a value that's realised. So, and through our work with industry in terms of, it's actually quite a common question, even before things like resource recovery and circular economy were mentioned as part of the purpose. It was more about, you know, we've got this waste, we've got a problem, there's something of potential value in it, can I make it, you know, part of our business to get something out of that waste and deal with the problem at the same time. So if we look at some existing cases, particularly the dairy industry is a really great example of where it goes back decades actually, is to where resource recovery and you could say circular economy, now that it's actually part of their business, to sort of think that at that time before it happened, you could say, you know, it's a circular economy approach, but basically dealing with the milk and the whey proteins after cheese making, they had a problem. They used to just dispose of it. It was regulated for them to stop doing that, and as a process of trying to deal with that, they now recover the whey proteins and now make a lot of money out of them. This is the same for lactose, biogas, we're already doing it, biosolids, and even if you just take wastewater that's got nitrogen in it and irrigate with that, you're actually recovering the nutrients already, and they do that already today. So what can we really learn about those situations where you could actually say, you know, there was an opportunity, they took hold of it, and you know, now it's actually utilised and dealt with the waste problem, you know, in a viable way. But where we are today is that much more needs to be recovered. So we're still dealing with, heard mentioned a couple of times that the issue is only just growing with us in terms of waste generation and pollution, and also the demand for high quality products. But often in any kind of situation why you can't do anything with your waste is because of the contaminants and also the fact that it's really quite dilute. So this is where membranes, as I mentioned, I promised I'd have a slide on membranes, can come to support a circular economy. And the thing about membranes is that you can pretty much separate most molecules from other molecules quite effectively, starting from macromolecules all the way down to ions, for example, you can partition. And particularly exciting type of separation I find is nanofiltration. Nanofiltration, just because you can separate sugars and minerals and partition in the minerals size range and also the charges. And the good thing about membranes and some of the projects I'm going to present, that the reason why there was an attraction to look at them versus other processes is that besides separating valuable materials from complex solutions, they don't change the material that you're separating. Other things like reaction, like you can use oxidation and so forth, you're going to change that compound. So you might actually render it useless or actually make it more toxic. So there's a challenge there. And also another thing too, and the project I'll talk about with the meat industry, the reason why there was an attraction there with membranes is because they use dissolved air flotation or a DAF, and they have to add chemicals to that DAF. It's also quite unpredictable, and so once you add those chemicals, you compromise the value of the materials that comes through that DAF. So this is where a membrane was actually quite practical. You still need to clean them. That's done separately to the actual processing. The market is growing, projected to increase from $10 billion worldwide to $10 billion worldwide from 6.4 billion today. And this is going to, due to pretty much the reasons that we're talking about, the things that in this hub is it's obviously for dealing with clean water and industrial applications and resource recovery. So where I am, so maybe you haven't heard of Victoria University. It's in Melbourne, just on the west of Melbourne. And I work for the Institute for Sustainable Industries and Livable Cities. It's directed by Professor Stephen Gray, so if you're in membranes, you'll be familiar with his name, or in water treatment. And now focused in Victoria University's industry collaborative research. Most, if not all, projects have some industry connection or industry partner. We look at membranes, but we also look at across the range of passive membrane separations, different membrane materials, inorganic, polymeric. I've looked at membrane distillation for quite a few years, but we also look at other processes, or oxidation, disinfection, applications in potable use, water recycling, and brine management. So the first one I want to talk about was herbicide recovery from wastewater. So this is an interesting project that we were put in touch with a company called Tritech Chemical, and they manufacture MCPA, which is 2-methyl oxyacetic acid, MCPA, and they were producing it, and there was a waste from that, and they weren't able to dispose of it and put it in the sewer. And so they wanted to see if they could recover that MCPA and continue processing it, and obviously dispose of the water because it was removed as the wastewater. There's actually and this is actually quite a typical situation that we will be faced with a challenge. We can talk about circular economy and resource recovery in the big picture, but when you get approached with a specific problem and you look for a paper as sort of guidance as to the science that might guide which separation you should use, there is, in this particular case, there's nothing out there. There's information about the toxicity and so forth, but there's no information about what you can do. So we go back and develop methods for analysis. We develop simulations for, in this particular case, reverse osmosis and nanofiltration, and even coined a new process called temperature swing reverse osmosis to look at how we can deal with separating the MCPA and also do it in a way that utilizes its solubility relationship with the solution that we're working with and temperature. And we ended up finding that these processes were successful, but the nanofiltration was particularly successful, and so the partner continued processing their waste with the process in the pilot plant. So this is one of our pilot plants, and dealt with their process. But we also found that you can enhance it through this TSRO process, and you can achieve your waste reduction to meet potentially meet the trade waste requirements of the utility. The next one, as mentioned before, were with the red meat industry. So this is a project with AMPC, Australian Meat Processor Corporation. So we took actually like a similar process to the way the dairy industry deals with its waste. They're pretty much, if you walk into a modern dairy plant now, there'll just be membranes everywhere. So they use microfiltration to deal with fats, they use ultrafiltration to recover proteins, and they also use reverse osmosis to concentrate and send off pretty much the only thing left at a modern dairy plant is the minerals. They take everything else out and can sell it for something. So, but the meat industry wastewater, which doesn't smell nice and is quite thick, like a chocolate McDonald's milkshake. If you're planning to go to McDonald's this afternoon, then you may change your mind, get a vanilla one instead. But it looks a bit like that. It's very high fat. These are grams per litre concentrations, not milligrams, and protein, very high. And this time we used a metal membrane. And the reason why this is quite a motivation, and we went to the site where we collected these samples, they spend a lot of money, trade waste charges, to deal with the COD, effectively the carbon that goes in down the sewer. So there's a motivation here to take what is effectively currently a waste, just redefine it as someone's trash as someone else's treasure, right? And so we ran this is a metal membrane. There's an Australian company that makes metallic microfiltration. This worked really, really well. And this is the waste that has actually gone through centrifuge decanting already, and can't be recovered with the current gravity processes any further. And so with the metal membrane, you actually concentrate it up more. We simulate another centrifuge decanting stage. This is their existing equipment. Put it back in, you get more tallow. And then we based an economic analysis on that and found that you can get some simple paybacks of a couple of years. So I've taken out all the dollar numbers, they're all there. I can give them to you, but just to put it on one slide. But you can pay it off the equipment within a couple of years. And in terms of trade waste savings, there was actually a big saving there. So if they can sell off their tallow that's recovered by this enhanced membrane process, they actually save themselves mostly on the trade waste charges. And we also looked at membrane installation and ultrafiltration again to recover proteins, but the big saver there was the tallow because of the tallow prices. Another one was firefighting, training, wastewater recycling. So this is we're approached by Arup, an engineering firm, to look at firefighting wastewater, which is heavily polluted and difficult to treat. So this is from the training facility, so not from normal fires. There's no water supply from putting out fires that you have to collect. It's from the training, so it's a reliable source of wastewater. And so this is very tricky. There's an example of it there. There's a tub of this oily water. It smells like kerosene and full of all sorts of things, including the foams that they used to put out. This is I guess a plane that they're doing some training to put the fire out. So we had to develop a big process train. We simulated all the steps in that train, and includes a ceramic membrane. Yeah, there's more information in that paper, but it effectively worked. And the key unit operations led to guided the design and construction of the plant, which you can go on YouTube. There's a video for it, and it's saving 30 million litres of drinking water per year. So the process worked quite well. They didn't end up using a ceramic membrane. They ended up using a polymer membrane. Yeah, so the separation is much the same. The next one is ammonia recovery. So we're sort of now on the topic of nitrogen. So it's fixed to take it from the atmosphere. Leads to 1% of the world's CO2 emissions, which is quite a lot for one thing. And this production of ammonia effectively feeds half the population, as far as I understand. It's a big number. So we're actually reliant on this Haber-Bosch process to produce the ammonia extracted from the air, and then produce our fertilizer. And then we pay money to treat it at a wastewater treatment plant to put it back in the air again. So this is the whole idea of closing the loop by capturing it while it's already fixed. So this is a project that was supported by funds from Intelligent Water Networks, and on site in the champion with Central Highlands Water in Ballarat. And so they run a fairly conventional water treatment plant. This is the sludge treatment process train, and they already take after the anaerobic digesters, they press out the sludge, and there's an ammonia-rich solution that they send to a lime dosing facility that actually automatically raises the pH. So the pH is sort of about 9, so it's ready to be liberated. Then we put vacuum membrane distillation on that, and we tried it just directly from the lime dosing and also with the struvite process upstream. Oh, thank you. I'll better hurry up then. I'm getting interested in what I'm talking. Okay, so we ran the vacuum membrane distillation and is the pilot plant, and it actually worked really, really well. Yeah, so we found out some practical challenges. Can talk to you more about that later. Now I'll just talk about our project. So this is nutrient minerals, and we're working with Parkway Process Solutions, and looking at some work that we've done before together on the AMES process. It's called AMES, which stands for Activated Mineral Extraction System. And effectively, it's a technology to treat concentrated aqueous solutions and recovers a range of valuable minerals. So you can take, besides fresh water, you can recover valuable minerals and actually produces the minerals as high quality products. And through the work we've done together and with what Parkway have done as well, in terms of checking out, evaluating the feasibility on potassium sulfate production. So we are working on currently on another hub. So this is the energy efficient separation, which will come to an end this year, at least for our project. And within that project, we enhance the AMES process to produce high purity minerals and is also energy and water efficient. And with that, we did some work in the lab and verifying some solution chemistry, and this allowed us to produce high purity sodium chloride, potassium chloride, leonite, which is a potassium magnesium sulfate, and of course potassium sulfate. Through these tests in the lab, we built a pilot plant. So basically did all the engineering, design and construction of this pilot plant, and with that it produced a whole range of these particular products that we were able to assess purity and so forth to demonstrate the feasibility. With the raw salt feedstock from salt lakes in Australia, Coringa Lakes. So what we're going to do on the hub, so our project is called an integrated water treatment process for valuable nutrient recovery and purification from industrial waste streams, and we align it, falls under theme 3, fertilizer optimization. We go for 4 years, and we've got our research team with Noel and Peter. That's myself. You already heard enough about me, and also our PI, Barhe Oskakmak from Parkway Process Solutions. And specifically, we're going to look at more broadly innovation, aeration, and membrane-based technologies, including the AMES process. We're going to further extend it with a nutrient recovery lens, and we're going to assess some industrial wastewaters for the potential, and target some contaminants to be removed, produce fertilizers, including potassium and organic-based, and obviously take the studies from also on the lab, and if we, depending how it goes, we'll be able to demonstrate that on our pilot equipment. We're located, so this is where my campus, where I am in Melbourne, so it's the west of Melbourne, and Parkway Process Solution is quite close, only 27 minutes drive, we work together and share facilities. So thank you very much, and this is a fond memory of the hub that we got a photo together, and we should get a photo together in this hub too. So yeah, so looking forward to working together. Thank you very much.
Thank you very much, Michael, for a wonderful presentation. Yes, your time. Can we have 1 to 2 questions? Some burning questions from the audience. Anyone? Oh yeah. Is somebody raising hand?
Yeah, yes,
Thank you very much. I noticed you're mainly working on some, at least pilot scale size.
Yep.
And I noticed in a couple of cases you focused on the membrane distillation. I'm wondering, for how long you can work it without wetting? Is it possible to run membrane distillation in any application, for example, ammonia recovery, for even though, for example, for a couple of weeks without wetting, or not possible? And second question, I noticed you mentioned one place you use ceramic membrane and another case metallic membrane. And I'm wondering why this one, not polymeric membranes? Is it really economical or not? Thank you very much.
Yeah, good questions. So for your first question on membrane distillation, we've run 3 pilot trials. The first 2, one was on a power station. We went for 3 months, no wetting. The second trial was at a textile factory in Wangaratta, and we ran it for about 3 months as well. With this one had weekend shutdowns to time up the factory, and we also cleaned the membrane with we did cleaning trials of sodium hydroxide and sodium hypochlorite, no wetting. So and the reason why is because in those papers there's a textile one in particular, because textile production you can have a wastewater that changes colour and property basically by the hour, right? So it's all over the place. So you have surfactants and you have all sorts of crazy things in there, right? So we use foam fractionation. So it's something that Lee mentioned as well, is foam fractionation to try and get surfactants out and the surface active agents, which is what foam fractionation does really well. But we ended up going with the most reliable way to avoid wetting was they already use an aerobic process to treat the wastewater, which is an oxidation basically. And at the end of that, the effluent is buffered because it's got a 2 days residence time, and it's treated with a biological process. And throughout the whole trial, we're feeding it with this water, no wetting ever. So yeah, that was just a hydrophobic PTFE membrane. Yeah. So yeah, you just have to make sure that you manage out the wetting risk, and it's fine. So 3 months, no problem in both cases. Yeah. The power station one was different. It was a ion exchange regeneration solution, so it's like sodium sulfate and tap water minerals. No problem at all. There's some organics, but nothing wetting. Yeah. And this metal and ceramic membrane. Metal membrane for the meat water, because you can do backwash pulsing. So you can blast off the really oily, fatty material with this backwash or steam backwash, which you can't do on a ceramic or a polymeric membrane. So that's why that worked really well. And you can clean it twice a day, doesn't care. Polymer membrane might last less, it's cheaper, there's these sort of things you've got to weigh up. But the ceramic membrane we use with the powdered activated carbon. So the ceramic membrane on the firefighting, we had a powdered activated carbon, and it filtered the powdered activated carbon. The process that got built used the granular activated carbon and polymer membrane. So we use powdered activated carbon because it's ceramic membrane because it's abrasive resistance. But you can avoid that in other ways and use a polymer membrane. So yeah, that was the reasons. But ceramic membranes, I have a report that shows that they can be cheaper than polymer, only in the specific circumstances. So yeah, depends on the situation. Yeah.
Thank you.
Yeah.
All right, thank you very much, Professor Michael Duke, for your presentation. So later on, if we have more questions, we still have some time after all the presenters.